All right, let's dive right into this explainer. Welcome, everyone. Today, we're taking a close look at an absolute engineering marvel, something that's poised to completely upend our understanding of the cosmos. We are doing an in-depth analysis of the Vera C. Rubin Observatory. For decades, humanity has peered up into the night sky, capturing these breathtaking but ultimately frozen moments in time. But what if we didn't just take static pictures? What if we literally filmed the universe? Over the next few minutes, we're going to explore exactly how this specific observatory is gearing up to shoot the greatest, most expansive 10-year cosmic movie ever made, and why this is an absolutely massive paradigm shift for astronomy.
3.2 billion. Yeah, you heard that right. That is the sheer, kind of incomprehensible number of pixels. 3.2 gigapixels packed into the camera at the Rubin Observatory. To put that into perspective for a second, it is the largest digital camera ever constructed for astronomy, period. It's so powerful that it's going to act as the catalyst for a completely new way of seeing space. We aren't just talking about an incremental upgrade to our current tech here. A 3.2 gigapixel camera allows us to capture the night sky with a level of depth and crystal clear clarity that was, honestly, impossible until now.
And hearing a number like that naturally leads us to a really vital question. What could we actually discover with a telescope that sees what others just can't? If you were taking a continuous, unbroken, super detailed look at the night sky every single night for an entire decade, what cosmic secrets are inevitably going to step out of the shadows? That is the core mystery we're unpacking today. By looking at the universe continuously, rather than just sporadically, we aren't just hunting for specific objects anymore. We're looking for the behaviors, the hidden patterns, and the actual underlying mechanics of the universe itself.
Okay, before we get too deep into those mysteries, let's ground ourselves in reality for a minute. Where is this thing? Well, this monumental observatory is situated way up on Cerro Puchon in Chile. It's a spot specifically chosen for its incredibly pristine dark skies. The whole operation is a massive collaborative effort funded by the National Science Foundation and the Department of Energy. And crucially, it takes its name from the legendary astronomer Vera Rubin. As we'll get into a bit later, naming this facility after her, it isn't just a nice tribute. It actually ties directly into the very scientific mysteries this observatory was built to solve.
When you break down the actual specs, you get a really clear picture of just how unparalleled this machine is. You've got an 8.4-meter main mirror to gather a truly staggering amount of light. Combine that with the massive 3.2 gigapixel camera we just talked about and an enormous 3.5-degree field of view. All of this hardware is entirely dedicated to one primary survey called the LSST, which is set to run completely uninterrupted for exactly 10 years. It's this specific recipe, the incredibly wide field of view, the giant mirror, and the ultra-high-resolution camera, all working together over a decade, that creates such a game-changing astronomical tool.
To really grasp what a 3.5-degree field of view means, just think of the number 45. A single, massive shot from the Rubin Observatory captures an area of the sky equivalent to 45 full moons packed together. Imagine going outside, looking up, and trying to cover the space of 45 moons with your hand. Now imagine capturing that entire massive area in a single, perfectly clear 3.2 billion pixel photograph. And then it just does it again and again, rapidly mapping out the entire visible southern sky.
Section 1. The paradigm shift from static photographs to dynamic movies.
So historically, astronomy has been all about capturing isolated static frames, but we are fundamentally transitioning from basic photography to full-blown cinematography on a cosmic scale. Think about the beloved Hubble Space Telescope. Hubble is absolutely incredible, but it functions kind of like a massive telephoto lens. It zooms way in to capture stunning static details of, say, a single bird sitting on a branch. But Rubin operates like a panoramic video camera that's continuously filming the entire forest. It doesn't just watch one bird, it watches the whole ecosystem move and change and grow over time. We're basically sacrificing the microscopic zoom to gain this incredible macroscopic awareness.
And the engine actually driving this macroscopic awareness is the LSST, which stands for the Legacy Survey of Space and Time. This is the actual 10-year scientific project being executed by the observatory's hardware. Every few nights, the LSST is going to map the entire southern sky. It sweeps across the heavens, taking those massive 45 moon-sized pictures, and then just a few nights later, it starts all over again. By doing this over 10 years, it creates a true, frame-by-frame chronological timeline of cosmic change.
The result of doing that is, well, it's staggering. We're talking about tens of millions of distinct images and literally petabytes upon petabytes of raw data. It's like moving humanity from flipping through an old, static, cosmic photo album to sitting in a high-def theater, watching the history of the universe play out as a true cinematic experience. The sheer volume of data this shift creates is going to completely dwarf anything the field of astronomy has ever dealt with before.
Section 2. The New Reality. Anticipated Cosmic Discoveries.
So, now that we know how it works, what exactly are scientists so incredibly excited to find in those petabytes of data? Well, because Rubin is watching the whole forest continuously, it is uniquely equipped to spot what astronomers call transient events. Basically, things that change, move, or explode. We're talking about supernova, these massive exploding stars whose brightness can spike for just days or weeks before fading out. With traditional telescopes, we actually miss the beginning of these explosions all the time. But with Rubin, because it scans so rapidly, we'll detect supernova almost in real time, which means other observatories can instantly turn their telephoto lenses right toward the explosion. It's also going to track variable stars, fast-moving comets, and, absolutely crucially, near-Earth asteroids.
But here's the really wild part. This observatory isn't just looking for bright, explosive things. It's also hunting for the invisible. And this is exactly where the name of the observatory comes full circle. The astronomer Vera Rubin famously provided the first robust evidence that dark matter actually exists by studying how galaxies rotate. Now the observatory bearing her name is going to take her life's work to the next level. By analyzing these tiny, slight distortions in the light of distant galaxies across its massive panoramic images, a neat trick called gravitational lensing, the Rubin Observatory is going to literally map the distribution of invisible dark matter across the cosmos. It's mind-blowing.
But hey, it's not all distant, abstract physics either. Because Rubin can see faint, fast-moving objects so effectively, it's fully expected to discover millions of new objects right here in our own solar system. And from a totally practical, Earth-saving perspective, it's going to serve as one of our greatest planetary defense tools. It will vastly improve our capacity to identify, track, and assess the risks of potentially hazardous near-Earth asteroids. This telescope could quite literally give us the early warning we need to save our planet from a catastrophic impact.
Section 3. Present day, a new data-driven astronomical era.
Even right now, in its early testing phases, the results are already proving that this massive engineering effort was worth it. The early test images have successfully captured incredibly dense star fields and resolved distant super-faint galaxies with just staggering clarity. But beyond just taking a pretty picture, these tests have proven the system's rapid data collection capability. The complex hardware and the absolutely massive software pipelines required to process this data stream, they actually work.
It really is the beginning of a new era of data-driven astronomy. And I want to emphasize that because these early images aren't just visually stunning. They represent a fundamental shift in scientific methodology. Astronomers aren't just going to be looking through an eyepiece or requesting a single image from a telescope anymore. They'll be writing algorithms. They'll be querying vast, ever-updating databases to find patterns in the sky. The astronomy of tomorrow is basically going to be as much about data science as it is about optics.
And honestly, that leads to a totally thrilling realization. History shows us that whenever humanity has drastically expanded the speed, the volume, or the clarity of our observations, we inevitably stumble across phenomena that we cannot currently describe. We built this machine to find dark matter, to track asteroids, and to watch stars explode. But that is just what we know to look for.
The biggest discoveries in the history of science, they are almost always the ones we aren't looking for. When you turn on a 3.2 gigapixel camera and you film the entire southern sky every few days for 10 whole years, you're absolutely going to capture the unknown unknowns. The bizarre anomalies, the weird flashes, the strange movements that just straight up defy all our current models of physics.
So, I'll leave you with this. What completely unexpected secrets will this dynamic, evolving universe reveal to us over the next decade? The Vera C. Rubin Observatory isn't just a telescope. It is an unblinking eye opening to a universe that is constantly in motion. We are finally ready to watch the movie of the cosmos. The camera is rolling, the data is flowing, and our understanding of the universe is about to change right before our eyes. Thank you so much for joining me for this explainer, and keep looking up.